2005 reinforcement learning. So we're going to be talking about learning a reward function with human feedback, and the application area is user-defined similarity search. So just to motivate this problem, image similarity search is pretty widely used. In Google, we can not only input text to get web results, but we can also input an image and get other images. In medical imaging and in Earth observation, satellite data imaging, we can input an image and say, look for other images that manifest a certain, condition seen in a CT scan, or say some environmental pattern that we see on Earth. And a lot of times, this is done using k-nearest neighbors, where we cluster similar looking images together. But this requires on some measure or metric like L1, L2 distance or cosine similarity. And if the human interpretation of what's similar differs from this metric, then we might need to look into some other solutions. So just, again, just to motivate this a little bit more, we can have similar looking feature, but most of this background is a beach, and then another similar looking feature, but most of the background is a forest. The k-nearest neighbors may not heavily weight that, but as a human, that may actually be the feature we care about. And so one possible solution here is to use reinforcement learning, specifically to build a reward function that helps in aiding to find these similar looking images that a user defines to be similar. So yeah, that's basically what inverse reinforcement learning is learning this reward function, not having a human crafted reward function, and then using your general reinforcement learning techniques on that reward, using that reward function. And so a couple of, this is just a couple of important papers. I'm going to keep this here just for a second, but I won't dive into it too much. You can pause it if you need to look at it, but I thought they were pretty important in the project. And so the specific task that I'm going to do is I want to build a reward function that highly rewards images that have coastlines. So basically the criteria when I was feeding in trajectories was I would prefer trajectories that had these kind of features that had both water and land. If it had all land or all water, I didn't prefer it. And tying it back to the image similarity search problem, using k-nearest neighbors, sometimes something similar to this could be land, sometimes something similar to this could also be water. But if a user is just, concerned about one kind of specific interpretation of this image, I thought RL could be an interesting avenue. And so to dive into the method, I used a pre-trained vision transformer as my feature extractor. We took the class token out of the last class token out of the vision transformer and then applied PCA to it. And I took two PCA components, and this is kind of the clustering that came out of that. And I used the min and maxes of these principal components to create a discretized 2D space. So this is how we got our states. And then we can see that it's possible multiple images fall into one state. And so that'll come into play later on when I talk about our trajectories. And again, to do this reinforcement learning with human feedback, in order to build a reward function, we do need to build a database that tells us which trajectory we prefer. So this is just kind of an example of what the trajectory looked like. I also had to build a really simple user interface in order to capture this data. So basically I'd be shown two trajectories, and then I would input a number for my preference, and then click the submit preference button and save that in the database. And then we go on to the next trajectory. And so what the database actually looked like, this is really just modeled after the 2017 paper. for each trajectory, we have trajectory 1, trajectory 2, and we say the state action, state action. 3 here just means I equally preferred both trajectories. 2 meant I preferred the second trajectory, and 1 meant I preferred the first trajectory. And so now in order to build this reward function, we have to choose a model, a function class. I chose logistic regression. It's a binary classifier with no reward or reward, so that kind of plays nicely. And we can also use a probability of the classification as an interpretation of the reward as well. So we have 256 states in action. Sorry, yeah, 256 state action pairs in this problem we've posed. And so this is what the logistic function looks like, where n is going to go up to 257. And so how do we actually connect this estimate of the reward to the trajectory? So this equation is based off a 1952 paper, and where basically we interpret this this kind of softmax looking function as the probability of preferring a sequence of images, and we say it basically depends exponentially on the reward summed over a trajectory. So that's what this equation is really telling us, and it's going to be used as an estimate of the human preference of one trajectory over another when we do our optimization. We're basically going to be trying to optimize a binary cross entropy loss. Again, this p hat of trajectory 1 over trajectory 2 is going to be the estimate of a preference, and this is the truth. So we basically optimize that using gradient update formula, and we get this loss curve. Logistic regression is nice because the objective is convex. And so yeah, I just use vanilla gradient descent here. There's a couple of questions as to why it just kind of evened out at 14.25, but I think the reward function still learned something, so we'll dive into that. So this is what the before and after of the reward function looked like. So before optimization, so before is on top. The rewards were not too spread out, a little bit more homogeneous. As we can see here, it goes from 0.35 to 0.65, whereas after optimization, there was a lot larger variance. So that's good in context of reinforcement learning, because we kind of want some, maybe like some decent amount of sparsity, but we also don't want like totally homogeneous rewards. So I think from a RL perspective, this method was promising to build a reward function. Now, we also need to look at what these states actually represent. So we'll get into that in just a second. This is a little bit more histogram view of how the rewards become spread out after optimization. And we can see here specifically on the bottom right corner, there's this tail that has some very distinct rewards. So that's part of this function learning. And we can see here, we got some high rewards in some small areas, and the variance increased by 3x. So again, I think that variance in your reward is important in learning. It helps the agent know where it should go to maximize the cumulative discounted reward. Cumulative discounted reward. And then again, going back to those states that had a high reward. So yeah, it's actually good. This state here, this reward here corresponds to this state, and there was indeed a coastal image there. This one unfortunately did not have any coastal images, but it was nearby. So again, there's some digging to do here as to like why some states did and some didn't, but it's good to see that the rewards were concentrated around the area where these coastal images are. And then there's many extensions. I think I'll just dive into 2 really fast. One is to have a simpler trajectory with just one state action pair and then a state. And so the rewards, the trajectories are not like drowning out any like reward that a human is really thinking about when preferring the two trajectories. And then I really wanted to get to doing a policy evaluation and policy optimization. And then also compare that to a handcrafted human reward. but just didn't get time to do that. But yeah, this was a quick overview of the project, and thank you for listening.